Okay, in this class we will look at the principles of generative modeling. So far in this course we have looked at the discriminative models. As I said, the in my mind the difference between a discriminative model and a generative model is that mathematically speaking both of them are distribution estimators. The fundamental problem of machine learning still is the estimation of the underlying distribution from its samples. However, in generative models, in addition to estimating the underlying distribution, one would also sample. The additional thing that is there in a generative model is that you sample from the underlying distribution. So, the problem with generative model is as follows: we are still given a data set which are n draws from an unknown underlying distribution. So, Px is still unknown. The problem with the generative models is that I will say that the goal of generative modeling it is linguistically not correct. If I say the problem with generative models, it actually means that generative models have a problem, and that is what we are looking at. So, what I wanted to convey was the problem that is being solved, right, using or with generative models is as follows. So, we will write that as goal. The goal of generative modeling is estimate Px from D and learn to sample, let us say learn to sample and sample. So, now this part which is sampling from the underlying distribution is unique to a generative model, and whatever we saw so far in this course are called discriminative models, in the sense that we do not explicitly learn to sample from the underlying distribution, but we only estimate the distribution. So, please note that when I say estimate the underlying distribution, all the parametric, non-parametric, implicit, explicit distribution estimation techniques that we saw in the course applies to generative models as well. So, there are generative models that would implicitly estimate the underlying distribution, explicitly estimate the underlying distribution. What is the difference? If you do an explicit assumption, if you make an explicit assumption on the underlying distribution and solve it through ML, right, they are explicit distribution estimations. The initial parts of the course we saw, right, you assume Px to be some P theta, assume a parametric form on it, and then estimate the underlying distribution through KL minimization. And there are implicit density estimators that we saw, which are like neural network and support vector machines or kernel machines, where you do not explicitly make a distributional assumption on Px and estimate the parameters, but you implicitly say that okay, there exists a hypothesis function, and that is estimating the distribution implicitly as a function, right. If you build a neural network, see, we now have the entire picture, right. If you take a neural network and solve it for a classification or a regression task, so train it for a regression or a classification task, what is it implicitly doing is estimating P of y given x, right, which is the conditional distribution P of y given x implicitly, without assuming an explicit distributional form on it and then trying to estimate the parameters. You do it implicitly using an underlying hypothesis function, right. Similar kind of analysis are there for generative models as well. There are generative models that would explicitly make an assumption on the distributional form and then sample. There are implicit models that would not explicitly make an assumption but still learn to sample, and so on. So, all those techniques still hold true, but by construction or by definition, all the generative models should have a capability to sample from the underlying distribution. So, that is the main goal of generative models. So, we saw, right, in discriminative modeling, depending upon what is the distribution that we are estimating, they have different names. Now, for instance, if we estimate the marginal, it is typically called the unsupervised learning. If we estimate the conditionals, it is called the supervised learning and so on, right. Similarly, for generative models some nomenclatures are there, and if you estimate, or if you estimate the marginal learn to sample from the marginal, so it is called unconditional generation. Okay. If you model the conditional distributions and learn how to sample from conditionals, it is called conditional generation, okay, conditional generative models. Now, I will give you examples of it, you are all using it today, right. See, if you in modern day AI, commoditized AI world, you can type a text and ask the model to generate a picture corresponding to that text, right. That is sampling from P of x given y, where y is a text and x is an image. So, that is conditional generative models. And also all the LLMs that you see these days, okay, they are all conditional samplers. Conditioned on the input text that you give, it will sample from P of x given y, where y is your input conditioning variable or the prompt, so called prompt, and Px will be the the distribution from which you sample. So, most of the LLMs that you see are conditional generative models. Unconditional samplers are the ones where you do not give an instruction or any conditioning variable, you do not specify a conditioning variable, but you just sample from the underlying marginal. So, this is the difference between generative models that are conditional samplers and the ones that are not conditional samplers that would estimate the marginals. Does it make sense? Okay. Now, see, there is an entire course that is being offered on generative models the coming semester. So, that we will discuss most of it in great detail, and we look at multiple families of generative models and see how they work and so on. So, this course is just to introduce the idea of generative models and show you a few examples of what generative models look like. Specifically, I am thinking I will discuss this class of models called adversarial samplers, or also called as generative adversarial samplers, GANs, and variational autoencoders and autoregressive samples, which are the samplers which are the LLMs, large language models. Only these three families, and that too at a very superficial level. We will not look at the complete math of it, just tell you the idea of how it happens and so on. Okay. Right. So, this is about generative modeling. You estimate the underlying distribution either implicitly or explicitly and learn to sample from Px. Okay. Any questions on the construction? Yeah. Distribution estimator.
But the thing is, whichever the hypothesis function is ideally the mean of the distribution, and whichever the last function you define is what determines what.
Agreed, that is implicit, no. What is the parametric form that the neural network takes depends entirely on the architecture and the parameters. Right. So, that way you are not making an explicit distributional assumption, right, on the distribution that is being estimated. Of course, it is done at the final layer, which is on y, but not at the entire distribution level. You do not make a distributional assumption on the marginal or the conditional and so on.
If we take MLP as the last.
That, yeah, that is irrespective of neural network, that is the same, right, irrespective of whatever architecture you take. The moment you take an MSE loss for a regression problem, you are assuming that the posterior is Gaussian with the mean being equal to the hypothesis function. That is correct. I am calling that implicit, it is a matter of nomenclature. I am calling it implicit because the hypothesis function, right, is not any parametric family, so to speak, that is it. Okay. Okay, so now let us look at what is the fundamentals of sampling is. Sampling from a distribution. See, the entire machine learning revolves around this one simple question, that I have given you samples from an unknown underlying distribution, estimate that. Estimate either the distribution or some parameters of the distribution, for instance the expectations or the moments and so on. That is the foundational statistical question that is being asked in all of machine learning. In addition to asking that question, in generative models we ask one other question, that how do you sample, okay. Now, this has been a question that statisticians have been asking for a long time, right. So, given a distribution function, how do you sample from it, okay. What do you mean by sampling? We will have to define the process of sampling. So, remember the very first class, we said that the only thing that is not defined in the entire gamut of probability theory is what constitutes randomness, right. So, after we define or after we say that there exists a random experiment whose outcomes we enumerate in a set called sample space, everything else follows, everything else is have precise definitions, measure theoretic correlates and so on. But what is not defined is what the underlying randomness is in the experiment that we conduct, right. Now, the process of sampling, okay, how do you define sampling? So, we said that generative model is a sampler. We have to define what sampling is all about, right. So, again that is something that cannot be, just like we cannot define what randomness is. Sampling is something that sort of vague in the sense that sampling is picking data points from the sample space. That is what you can. So, you have a sample space that is constituted from a random experiment, okay. You pick samples or pick data points or pick elements from that set. So, you have a set which is called the sample space. If you pick elements, okay, that governs the underlying probability measure. You have to pick the elements from the sample space respecting the underlying probability measure. This process is called sampling. What is generation after all? So, we have, so if I have to go back to the non-mathematical way of saying it, that you repeat the underlying random experiment is what I should say. It is given a distribution. So, it is sort of an inverse problem in the sense that we do not know how to conduct the random experiments. We have given the outcome of the random experiment and the entire story you know. So, we have the outcome and on top of this outcome we have this function called random variable, and what we measure are the elements in the range space of this random variable. That is what we have as data. You know, we are coming the full circle, right. Remember what is our data? Our data is the elements, or data are the elements from the range space of this function called random variable, okay, whose domain happens to be the elements of the sample space, and the elements of the sample space are simply the enumeration of the outcome of this random experiment. Now, we trace back the problem. So far what the problem that we are interested in is that given that we have the elements of the range space of the random variable, estimate the underlying distribution. Now, why is that of importance? We saw why is that of importance in all the discriminative problems that we solve of assigning a label, regressing, etc. All of these are distribution estimations, we saw that, okay. So, the underlying problem was given the samples from given the data points from the range space of this function called random variable, which is tied to an underlying sample space with a distribution, estimate the underlying distribution. Now, we are saying given this data which are elements from the range space of this random variable, function called random variable, you give me more elements from the range space of the random variable, which goes back to saying equivalent to saying that you give me more elements from the, pick the elements from sample space such that the underlying probability measure is respected. So, this is said you will have to sample in accordance with the underlying distribution. I will tell you what that means. So, let us say that I ask you to sample from a distribution of MNIST data set, okay. Now, if I model the MNIST data set, imagine that the MNIST data set is a yeah, it is a Gaussian distribution, okay. I mean it does not follow a Gaussian distribution, let us say it follows a Gaussian distribution. So, in that case any image, okay, with any values in the pixels constitute a sample from the Gaussian distribution, right, because Gaussian distribution has infinite support. However, we want that does not constitute a good generative model. So, now the question is what constitutes a good generative model and so on. The question that we are asking is we have to sample in such a way that the exact distribution that we have for the underlying data is respected. In other words, what do you mean by distribution on data? We already know that, right. I mean suppose we have 100 pixels in or 100 dimensions in data, a distribution over those 100 dimensions only mean that with this likelihood we get this value for this particular pixel and so on. So, when we sample we will have to get a vector that would precisely obey this underlying likelihood rules for the distribution. That is what is meant by you sample in such a way that the underlying distribution is preserved. Do you see the point? This is very important because you have to understand what sampling is. You know, sampling at the outset is getting and repeating the underlying random experiment, that generated this particular distribution and random variable. But we do not have access to the, we neither have access to the distribution nor we have access to what the underlying experiment is. All we have are the samples of this function called random variable, the data points from the range space of this function called random variable, we have to work with it. Is it clear what sampling is all about? Okay. Now, what is our starting point? You know that our problem is to now get data points from the range space of the random variable which obeys the underlying distribution. What can be our starting point? How do we even go about sampling from an underlying distribution? So, this is a topic, okay, that is often studied in computer science called random number generation. So, what are these? These are samplers from uniform distribution. The starting point for all generative modeling is that we assume that we know how to do this. This is taken for granted. So, we assume that we know how to sample from uniform distribution. Okay. Okay. So, I am mostly talking about sampling from marginals. When we talk of sampling from conditionals, there is a slight variation that will come up. Well, we will talk about it later, but we assume that we know how to sample from a uniform distribution. Okay. I keep joking that the biggest irony of computer science is that we have deterministic algorithms to do random sampling. So, there are multiple algorithms for random number generators which are samplers from uniform distribution. So, we assume that we know how to sample from uniform distribution. Let us say that Z, so Z is sampled uniform from a uniform distribution that is uniform between 0 and 1. We just assume that we know this, okay. So, this is assumed to be known. Okay. Now, we have some seed to start with, so that we know how to sample from uniform distribution. Then we will invoke all the probability theory that we studied to solve the actual problem of sampling from unknown distribution. Now, tell me, this actually you all know this. Given that I have samples from one random variable, now the question of sampling from an unknown distribution can be cast in a different way. Now, we can say that given that I know how to sample from one distribution, tell me if I can sample from another unknown distribution. Initially, the problem was given data from an unknown distribution, sample from it. Now, the question is given data from an unknown distribution and the fact that I can sample from an underlying known distribution. Now, tell me how do I get sample from this unknown distribution given this setup is the question. Okay. Do we know the answer for it? What is the answer? Huh?
We estimate that distribution using the method that we saw
And
then use the non-sampler to somehow.
that somehow is the actual question, right. So, how do you do that somehow? We do not even have to estimate the underlying distribution, right. Any other answer? Inverse CDF is one definite method to do it. I mean, the answer is there is something called an inverse CDF method, right. So, generalize the idea of inverse CDF. What is inverse CDF? There is this theorem that says that the distribution of the cumulative distribution, this distribution of a random variable is always uniform. What do we mean by this? You take a random variable, define a function on top of it which is the so called CDFR distribution, right. Now, that becomes another random variable. Now, look at the distribution of that random variable, that is uniform, that is a known result. Now, you invert that. So, now it means that starting from a uniform random variable you can always invert it. If you take a random variable, if you take the CDF of a random variable and invert the CDF as a function, then the corresponding random variable will have the distribution of interest. So, this is called the inverse EDF method. We will not go there, okay. So, this, since you mentioned the name, I just wanted to complete the story, abstract it out. What is the abstraction of inverse EDF? Why is that the inverse EDF method works? So, here is the idea. Now, suppose z is a random variable, let us say that g of z is a function from space of z to x, okay. So, g is a deterministic function, let us call this as g theta of z, okay. Then x cap, let us call this as, yeah, x cap is equal to g theta of z for z coming in uniform 0 1, okay. Now, g theta is a deterministic function. What we do is we take samples drawn from a uniform random variable and pass it through a parametric function g theta. Now, we know that the distribution of g theta of z is different from the distribution of z, right, correct. Why? You take a random variable, do a deterministic transformation on top of it, the distribution of the output random variable is different from what the input random variable is a standard result. All of you know this, right? It is called functions of random variables. If you take a random variable, define a deterministic function on top of it, you get another random variable. Function of a deterministic function of a random variable is always a random variable. Why is that? See, random variable is a composite. Remember the first class, right? Random variable is not a variable, it is a function. So, there is a set sample space, there is a function on top of it which is your random variable, the function itself is random variable, and if you define a function on top of it, what do you mean by defining a function on top of a random variable? Composite on what? So, what is the domain of this composite now? The range of the random variable, the range of this random variable becomes the domain. So, when you sample from a uniform distribution, what you get is the range of the elements of the range space of this z. On top of it, you define another function that becomes a composite, and therefore it is another random variable, because you can always define the inverse. So, from g inverse takes you to x and x inverse take you to the sample space, which has an underlying probability measure, and therefore the composite of a random variable or a function of a random variable also becomes a random variable, because there is an underlying probability measure, but the distribution changes depending upon what your g theta is, correct. Now, the idea is very simple. What do we need? Now, let us call this distribution, suppose the distribution of x cap be p yeah 1 theta 1 x cap, we need both of them, right. So, p theta x cap, okay, let me write it a little more, okay, p theta x cap, I will write it this way, okay, p theta x cap. Now, if we can find a theta, okay, that would minimize the KL divergence between px and p theta, then g theta star of z is a sampler for px. Do you agree? Suppose we find the parameters of this transformation function g theta such that, oh sorry, this should be a, this does not mean anything. So, some divergence measure, right. If I take the divergence measure between these two distributions, okay, and find the theta in such a way that this divergence is minimized, then g theta star of z is a sampler for px, isn't it? Do you see this? Why? So, now what is the final sampler for px now? Take this function, take sample from a uniform distribution, pass it through this function g theta, and whatever the output is are the samples from Px. Do you see this? So, this is the foundations of all generative models that you see. The questions are what is the form of g theta that we should use, what is the divergence measure that we will be looking at, and how to solve this optimization problem. The same questions that we ask for discriminative models. Okay, I will spend an entire course on like answering these three questions: what d, what g, and what is the optimization problem that we are solving.
Any constraints that are there in something optimization?
Why do you need a constraint? Depends on what choice of g theta that you make, right? Sometimes mostly that it's unconstrained, right? So there's no, because you want to estimate the underlying distribution. Any questions on this formulation? See, what did we do? We wanted to sample from an unknown distribution Px.
First question is it correct that the distribution CDF of the distribution of any random variable is uniform?
I am not talking about that, just forget about it. That's the, yeah, that is correct. Yeah. So see, g theta is any function, right? So the statement that I made is take a random variable, pass it through any deterministic function, you get another random variable. Now, if that deterministic function is the CDF function, so what is CDF function? It's an integral, no? You take the random variable and then compute the CDF function, that becomes another random variable. So the distribution of that random variable is uniform irrespective of what the input random variable is. That's a different result. So that's, and then you invert it to get the distribution of interest is the inverse CDF method. I am not talking about the inverse CDF method at all. Right now this is the, in fact inverse CDF method can be seen as a special case of this, we will not get to that now. The statement that I am making here is the foundations of all generative modeling is that you assume that you know how to sample from a uniform random variable or any other random variable that you know how to sample from, and learn a function on top of it such that the transform random variable will have the same distribution as that of the distribution from which you want to sample, right. How do you do that? Is by minimizing the divergence measure between the actual distribution and the distribution that this function is imposing, that is it. Now again the same questions exist, right. We do not know Px and we do not know what, in some cases we do not even know what P theta is, right. So now how do you get P theta, how do you solve these optimization problems are the details that we will work out, but the foundations, the idea, the underlying idea is this, that you start from see what changed from the generative modeling and the discriminative modeling is that in discriminative modeling we do not start from an arbitrary uniform random variable, right, but here we start from a arbitrary uniform random variable and then we transform it into distribution of interest, that is it. See, a sharp mind will ask now, right, suppose your g theta is a neural network in discriminative case, x is still a your input data which the neural network takes is still coming from a random variable, right, because it has a distribution. Now that can also be seen as transforming a random variable, right. So why is a discriminative model not a generative model? That is why I keep saying that every discriminative model is a generative model that would sample from this conditional distribution, because it is transforming a random variable x to a random variable y through a distribution through a deterministic function which is a neural network. So that way even discriminative models are generative models which are samplers from P of y given x, right. But here we are sampling from P of x, the marginal. The way we do it is start from a uniform random variable, take its samples, transform it through a deterministic function and set the parameters of the deterministic function such that a divergence measure between what the output of the deterministic function gives and the underlying distribution that you are trying to measure, that is it.
Here Z is the data point.
No, x is the data point that we have, z is samples from a uniform distribution, c are samples from uniform distribution, people call it noise, right, or the random seed or whatever, right. So you have I mean to me it is just transforming one random variable to the other, that is it. Any other question here?
So do we assume that every Z has a corresponding data point?
Where? No, we are not at all assuming. It's only a distribution level matching.
Some Z can give us data which is not part of.
It should give, no. Otherwise, if it just learns a one-to-one map from some data points from Z, or rather this distribution, that it's not a generative model. Generative model is the one that learns how to cover the entire that is why we are matching it at the distribution level, not at a sample level. And also remember that we are sampling from a continuous random variable, right. So there are there are infinite samples. The set is this, the cardinality of this set is infinite, right. So otherwise it will just remember whatever is there and then just map one point to that. Is not what a generative model is. We need to estimate the entire distribution, so that when we sample the points that we get, right, are not from D. It should not be from D. So that is why when you ask some of these generative models today to generate a picture or something, it will not generate something that you already know. Right. So one fun exercise that I always ask my students to do in my generative modeling courses, to open a particular website called thispersondoesnotexist.com. Right. So every time you refresh that website, what's happening is you get a picture which is nothing but you take a Z from a uniform random variable and pass it through a particular G theta which is called a style GAN, and you obtain an X cap and display that. That's it. And that person does not exist because you are sampling from the distribution of human faces, and you get a picture that is, I mean, if your G theta is good enough and if your optimization technique is good, then you will estimate Px properly. So now the question is, how do you evaluate these generative models? Remember that even for evaluation we do not have Px, all we have are still D. So but in discriminative models what do? We take D, we partition that into training and test data, and we have metrics to do that. Similarly, we have metrics to compute. This is something called FID and so on, which I will talk about maybe in the next class. So there are metrics to evaluate how good a generative model is, but the idea is distributional level matching, not a one-to-one point level mapping that is to be done. If that is what happens, then it is a very bad, it is actually the overfitting case of generative modeling, right. Yeah.
In the rare case, we might end up sampling one of the data points. In that case, the person exists.
Yeah, because you are talking about data in some tens of thousands of dimensional space, right, sampling from it, what the odds of, you remember that thing that I said, no, the odds of hitting that one particular point. In fact, we all know that if the random variable is continuous, then the probability of obtaining one particular point is 0. That is it. So that is why it is almost always you do not get it. That is why even with LLMs, right, every time you give the same prompt, it will give you different answers because it is actually sampling from the underlying distribution. See, LLMs are samplers for the entire universe. This Px is the entire universe. You take the entire universe, distribution of entire universe, D, make your D trillions of samples and use the same techniques to learn the underlying distribution. Any other question on the philosophy of our generative modeling? Yeah.
We take a uniform distribution always and map it to the random variable.
Distribution of interest. Yes.
We map it to the data.
Distribution of interest. You take samples from uniform distribution and map it to the distribution of interest, data, whatever distribution that you are trying to model. This is for unconditional generation. We will get to conditional generation in a while. Yeah.
How do you extend this concept of sampling to multi-dimensional?
No. This is still multi-dimensions, right? All your random variables are in RD, right? Yeah. So these are okay. I mean, I wrote universe of 0. See, I can actually, I mean, to make it general, I can always make it a k-dimensional uniform random variable from, and this function is from this is how it happens typically. Start from a k-dimensional random variable uniform and map it to a d-dimensional random variable, which is what we have. Okay. Anything else? Okay. Actually, we already know a few techniques to do this. I have been using this. There is a function called rand n. Do you know this? It is, what is this? What does this do? You know what this does? So, RAND is a random number generator which is sampler from a uniform distribution. What does rand n do? Sample from a Gaussian distribution or a normal distribution. What is it doing? We are already sampling, we know how to sample. So, perhaps you would have already studied in your probability theory course that there is a function g that would transform a uniform random variable into a Gaussian random variable, right. What is it called? There is a name for it, no? I do not recall the name. So, it has some e power square root of this thing or that I do not remember the exact form, but there is a deterministic function that takes a uniform random variable to a Gaussian random variable, right. Now, we know how to sample from a Gaussian random variable as well. So, suppose you need data, okay, that has infinite support. Start from sampling, start from a Gaussian random variable and then transform it. Is that all right? Okay. So, now for those random variables which we know what function gives us, what transformation gives us this random variable, then we can come up with a deterministic random variable. Okay. But for arbitrary distributions, naturally occurring data, there is no way that we can come up with this sort of a function. That is why we resort to this divergence minimization to do this. Okay. So, let us look at a few methods to solve this problem. As I said, because these lectures are very introductory, I will not derive this from first principles, I will take a top down approach, which is very atypical of this particular course, where I will tell you the algorithm and hand wave the math. It is always the other way around, right. So, we will do the algorithm, the math and then hand wave the algorithm, it is the other way around now, okay, because there is an entire course that is coming up where we do everything from first principles. So, let us look at this first class of algorithms which are called adversarial networks or generative adversarial networks. We will stop here and continue in the next lecture.